Hello everybody, welcome back to another Strengths Materials video. And in this video, we're going to be talking about slope and deflection and how to solve for it in a simple cantilever beam like so. We're going to be using the slope and displacement by integration method to make this possible. Now, this method is great for solving for slope and deflection because it allows us to create relationships using moment and shear equations that we've learned previously in our method of sections videos in order to integrate towards the slope and deflection of any point on our beam. And this all starts by first imagining what the elastic curve looks like for a member. Now, what is the elastic curve if we don't remember? Well, it's basically the predicted deformed shape of our member. And it uses the assumption that the deflections will be very small for our member, meaning that we remain in the elastic phase during loading. Therefore, we can then employ the elastic curve. Now, in our problem, we have a cantilever shape that's loaded with this triangular distribution. And we can assume that the most severe point of deflection is going to be at this very end point, right? Now, if we imagine that the deflected point is going to be somewhere around here, that max point right there, then we know that we have a fixed support. So we can imagine that the elastic curve will follow a shape like so to meet that deflected point at the end while not deflecting at the fixed support. Now that we have our elastic curve, let's actually take a closer look at what's going on at this max point of displacement right here. Now that we're zoomed in, if we took a tangent point at this max deflection on the elastic curve and compared it to the original undisplaced neutral axis, or the x-axis in our case, then we can take an angle between that tangent and that original axis, which is allowing us to develop our slope. Now, relating this slope to a equation, we have for an infinitesimally small point, the slope will equal to our first derivative of y with respect to x, where y is that difference between the tangent and our original undisplaced axis and the length of our segment. In other words, this also means that we now have a relationship between deflection, which in this case would be dy, and the slope, which is the first derivative altogether. Now, what if we don't know our slope? We can't really do much with this equation. Now we need to create a relationship between the moment and deflection. And this is going to be done by considering the moment curvature equation. Now, to visualize what this relationship is actually trying to tell us, we have to look at some circles. And the best way to do this, I think, is just to take a look at the elastic curve. And as we increase our slope, we are actually going to be creating a larger radius of curvature, which means this circle is going to be much larger, and this r value is going to be much larger. So r is the radius of curvature of the deformed shape. And we've already mentioned that m is going to be the moment at a specific point of interest, and the EI is the flexural rigidity. Now let's recall again, we have the E, which is Young's modulus, which is just the material property relating the stress applied to the strain developed in the elastic region. And the I is the bending resistance, which is a geometric property of the member. Now, mathematically, curvature can be solved by a complex equation. And that equation for curvature looks something like this, which is an absolute mess, and dumb engineers don't want to work with an equation that looks like this. So we have to go back to our original understanding, right? What did we say at the beginning? We imagined that the deflections will be very small for all of our analysis, which also means that the slope at any given point should also be very small. And what do we recall? We recall that the slope is equal to dy over dx. So if you plug that in down here, and then we square a very small number, we can then assume that this value is actually negligible, which allows us to simplify this equation. Once this equation has been simplified, we're left with the curvature equaling the second derivative of our deflection. And we can then go back and plug that into our original curvature formula. Now that all of that is cleaned up, we now have a final relationship which has been reorganized for m, which allows us, in simple terms, to integrate this function twice in order to determine the deflection based on the given moment. But let's not stop there. We can also create relationships between the shear and the given applied loading. But we have to recall some of our relationships from previous videos for bending moment diagrams. Now let's do this recall here by bringing back those equations from those videos. And the first one we're going to look at is dm over dx, which is equal to v. And all this means is that the slope of the moment diagram is going to be equal to the shear. So whatever that relationship was, they are going to be transferred into each other's diagrams as a relationship. And that relationship is shown right here. For this beam configuration, we have a negative constant value of 2 for shear, meaning that the slope of our moment diagram is going to be negative and constant. So it's a linear line that is negative and constant, right? So if we take this relationship and then apply it to this equation, we have moment here, and we have the derivative of moment here. So we can work backwards in order to get this in terms of shear. Now let's see what that looks like. So all I'm doing here is taking that relationship and taking the derivative of this moment and seeing how that applies to the other side of the equation. So as we derive this, we also have to take the derivative of the other side, meaning that we will now have this integration to the third power. And we recall that dm over dx is equal to v. Therefore, we solve that the shear will be equivalent to the 3 times integration of this side of the equation. And we have a very similar relationship with the distributed load function as well. So now that we have all of these equations derived, what do we need to know before hopping into the problem and applying these equations? The first thing is we have to understand compatibility conditions and support conditions. Now, what does that mean? All that means for now is that if you have something like a fixed support, then you know that the slope and deflection will be 0 at this point. And you know if you had, let's say, a simple beam and you had the max deflection at the midspan, you're going to have your max deflection but 0 slope. We're going to see how those relationships apply to our actual problem. And another key understanding for these problems is how to analyze a rigid body using the method of section or the cutting method. And if you want to recall to that, we can take a look at the link above. And all that means is that we have to take segments of our member in order to determine equations based on an x value in order to solve for the moment at shear and shear at specific points. Now let's start solving this problem. Now, a good way to start any of these problems is always to go for the reactions. So we know for this cantilever that we're going to have a resisting moment reaction here. So let's call that moment of A. And we have these forces acting downwards, which means we're going to have an upwards reaction at the support. And we'll call that R at A. Now let's first solve for the moment at A. And that's simply done so by taking our equilibrium equations and using our sign convention here. And simply plugging this in, we have the moment at A that we're starting with, and that's going to be positive based on our convention. And we have this resultant force from the triangular distribution. So if we drew an estimate of where that is going to be acting, we have that FR here at a distance away of 2/3 of 9. So 2/3 of 9 is going to give us 6 feet. Now let's start plugging in these values. We have, obviously this is going to be creating a clockwise rotation, so this should be negative. We have the FR, which will be equal to 1/2 for a triangular distribution, the magnitude of the distribution, which is 3, and the length that it covers, so that is 9. And then since we're taking the moment, we have to also consider this distance of 6 feet. Now, plugging all of that in, we will be left with a moment of A of 81 kilonewtons. Sorry, I live in Canada. Kip feet. And similarly, we do the same thing for Fy. and we are doing the positive being upwards, and we have only two forces here. So we have that reaction at A, which is positive, and we have this downwards acting resultant force, which is represented by this right here. So 1/2 3 times 9. Solving for that, you have RA, which is equal to 18.5 kip. Now let's take a segment of this member in order to solve for some equations with respect to x for moment. Okay, so now that we've taken an arbitrary section with our reactions solved for, the first thing we need to do before solving the moment equation is, what is this W? And if we remember from previous videos, whenever we have a triangular distribution and we're using the section method, we have to create a relationship based on what's given. So we have 9 feet originally related to a 3 kip per foot, magnitude of the distributed load. So in our case, for the section at a length of x, we have an unknown distribution of W. Therefore, solving for that, if we had W over x is equal to 3 over 9, then we can simply say that our W will equal to 1 over 3x. Now we can go ahead and plug it into our following equation, where we are taking the moment about this cut and equating it to 0. Now, what is this going to look like? We have a lot of different things to look at. First one is obviously the moment at x, or our point of reference. So that is going to be, based on our convention, positive. So we have a moment at x here. And then following that, we have to look at this resultant force. And this is broken up into a couple different terms. The first one being that it's 1/2, obviously, for a triangular distribution. We have the magnitude of the distributed load, which we solve for is 1 over 3x. We then follow that up with the length, which is going to be x. And then we have the distance away from the point of reference to that resultant force, which is 1 over 3x. And the last 2 points that we have are this moment here. We have to simply add 81, and we have this 18.5 at a distance x away, and that's acting clockwise. So we have negative 18.5, and that's times x. Now bringing this over, mx, we're going to have this turn negative, meaning that all of these signs are going to flip, which will leave us with an equation that looks something like this. We have 13.5x minus 1 over 18, x to the power of 3, 1, 2, 3x is there, and we have this 81, which is now a negative. So now that we have this moment equation, we can now plug it in for our relationship to deflection. So we simply have that EI, d squared y over dx squared, will equal to the exact same thing on the other side. Now, why is this important? This is important because now we can finally start integrating and work towards the slope and the deflection. And the first thing that we can do is take the integral of this equation in order to get this in terms of a slope equation. And then the next equation, we do the same thing, but to get it in terms of deflection. So let's see what this integral is going to look like if we took this equals to dy over dx. We have to integrate everything on this side. So we follow simple integration rules. So this is going to be 13 over 2, and we're adding 1 to the exponent here. Similarly on the side, we have 1 over 18, and then this x to the 4, and then this is going to be over 4. And then we have the minus 81. We're adding that x component, and we also have an unknown constant. Now, if we simplify this further, we have something that looks like this. Now we can do the exact same thing here and take the integral of this equation to get the deflection. So if we say deflection is in terms of y, then we would have something that looks like this. We have 6.75. Now this is over 3. This x is going to be to the 3. We have 1 over 72. This is going to be x to the 5 over 5 minus 81 over 2. And that's x squared now. plus C1. That's going to be an X beside it. And we have the C2. And then simplifying this equation, we have something that looks like this. Now, how can we move forward with this equation? We have to create some boundary conditions in order to eliminate or figure out what these unknown constants are. So let's take a look back at our cantilever. Alrighty, just had to clean this up a little bit. Looking at the cantilever, we know that at this fixed support, we have no deflection and no slope, right? So if we write down this relationship on the right over here, we can say that when x is equal to 0, we have this relationship here, dy over dx, which is equal to our slope, is equal to 0. And we also have that our deflection is equal to 0 when x is equal to 0. Therefore, if we plug this into our equations, we can then solve for these constants here. And luckily for us, when we plug in that slope equals to 0 when x is equal to 0, we solve that C1 will also equal to 0. And then similarly, when we have that the deflection is equal to 0 when x is equal to 0, we can solve that C2 is also equal to 0, luckily. But in some cases, this is not always true. Your constant will not always be 0, so you just have to be careful of that, okay? Now, the last important point is going back to our elastic curve, remembering that the max slope and the max deflection is at this furthest point of the cantilever, which is at 9 feet. So now all we need to do is plug in for these equations for slope and deflection at 9 feet. So if we took this at 9 feet, we would have something that looks like this. We have 9.75, 9 squared, 1 over 72, 9 to the 4, minus 81 times 9, and this is equal to 0. We would then solve this and get a value of, just looking for it on the side here, 273.375. And we have to remember that this EI has to be brought over in order to solve for only slope. So we have this all over EI. And then this is going to be in kip foot squared. And we do the same thing on the bottom here, where we're just plugging in that 9 foot, where that max deflection is going to happen. Now we're pretty much done this problem here, but the last thing that we need to do is figure out what these EI values are in order to get this in terms of slope and deflection for this specific member. So we're given that the E is equal to 29 times 10 to the 3 KSI. And for this W section, it has a unique moment of inertia value, and that is going to be about the strong axis or the x-axis. And that's going to be 29 or 291, sorry, inch to the power 4. And plugging those values in, you'll be left with a slope at the max point of 0.0047. And we know that based on the elastic curve that was here previously, this is going to be a rotation like so in the clockwise direction. And this will be in radians as well. And for the deflection, we have a very similar thing. We have a negative value, but also the deflection based on our elastic curve is downwards with respect to our original axis. So we're going to have a downwards deflection. We know that. And plugging in that EI value, we will be left with a deflection of 0.369 inches. And those are your two final answers for slope and deflection. And I hope this helped. Thanks for watching.